Hey guys, I hope you had a great Memorial Day weekend, and I want to start section 3 in chapter 8, partial fraction decomposition. Now, this sounds very intimidating, but what it is breaking down our rational expressions, rational equations with addition and subtraction. Just kind of like how you factor to get um, linear terms of a polynomial. Partial fraction decomposition is breaking down a rational expression into what the two have. So to better explain this, I have what we already know over here to the left. So the idea behind this is if I have 3 over x plus 2 plus 5 over x plus 1, we couldn't add these together because they don't have like denominators. So what I'd need to do is get a like denominator, multiplying each denominator to each other. So multiplying 3 over x plus 2 by x minus 1 and x minus 1 by x plus 2 to both the numerator and denominator. Remembering to then distribute, so I have 3x minus 3 and 5x plus 10. When I taught you, we did it all under one denominator, but now that they're like denominators, you can combine like terms and we'll end up getting one denominator, and we'll have 8x plus 7 over x plus 2 times x minus 1. Now, what we did is we would then simplify that denominator to be x squared plus x minus 2, but you can, in this examples and what we do here, we can just leave it. So what we started with is in yellow, and this is what we ended with. With partial fraction decomposition, we're actually doing the reverse. So we're starting with our rational expression, and we're trying to break it down into addition of two distinct. Notice how I'm saying the word distinct. Distinct means unique. So unique x linear terms. So we're going to focus on two different types. There's multiple, so I'm going to kind of show you those rules. But again, here's that example. What we end up getting, we always want to make sure if it's not in factored form, we want to make sure it's in factored form, and then we're going to get two fractions. These two fractions on the right are called your partial fraction because they are part of the whole over here. The sum becomes your addition, and this is our partial fraction decomposition. So this is your goal in the end, to get the addition or subtraction. In this case, we're going to keep writing it as addition, but notice you could write it as subtraction because it's plus a negative, and you could really write it as subtraction instead of plus a negative, but we can just keep it as addition. So the rule for partial fraction decomposition can be written for rational expressions of the form p of x over q of x. That should seem somewhat familiar from the beginning of the year, where p and q have no common factors. If they do, we're going to cancel those out. The highest power in the numerator is less than the highest power in the denominator. We used to call that bottom heavy, and you can still refer to it that way, but you can't do this unless the expression is bottom heavy, that the denominator is at least 1 degree higher in the denominator. And whenever we're doing this, the denominator must be in factored form, so if it's not, we have to do that ourselves, and it determines the type of partial fraction decomposition. So again, if I was given something like this, I would need to break it down into its linear factors, which I did. And since these aren't the same, it's not x plus 4 and x plus 4, these are distinct linear, it'll show us what our partial fraction decomposition is going to look like. And so to set this up, here are our rules. Now this looks like a lot, but in today's video, we are going to focus on really 1, 2. I'm not going to show an example of 3, but just so that you're aware. So like if you have two linear factors, we're going to write it for some value a over x minus whatever your factor is, and x minus b. It could be x plus, just as we've seen before. When you have a repeated factor, so this would be x minus a times x minus a, you just write it once and then again with the square. If you have more than two factors, a lot of time we only deal with two, but if you had 3 linear factors, you would just keep going a, b, c, d, all the way to z technically. And in our next video, I'm going to talk more about quadratic factors, but for right now, we're just going to deal with our linear factors. So let's get into an example. If I were you, I'd pause this, maybe take a picture, jot this down, take a screenshot of it, so that you have this as a reference point for yourself when you're doing partial fraction decomposition. I know it's a little wordy, but it sounds impressive. So, well, you can now see what's going to happen. I didn't hide everything. So this is how your problem's going to start off. We'll have something in our numerator. The denominator is a degree higher. And sometimes it'll be in factor form, sometimes it won't. So let's first factor this. When we write it into our factored form, that's our first step. And based on my rule, because I have two linear factors, they're not the same, what I end up with is A over my factor, B over my factor. The order does not matter. We know that with addition, order doesn't matter. So however you want to set it up. So again, our first step is to make sure that the denominator is factored and we have linear terms. We want to then write out our partial fraction decomposition, as I just said. The reason I know to do that is from this rule over here. Again, I'm getting it from this rule, knowing I have two distinct factors. There's nothing being repeated. They're not quadratic. We'll talk a little bit more about that later. So, okay. So our second step is to write the partial fraction. So we're going to take our expression and make it into an equation. So I'll have x plus 7 over x minus 3 times x plus 2. And then I've taken my factors, broken them up as a over x minus 3 plus b over x plus 2. Our third step, and that's why this was here. Sorry, I didn't get rid of that. But multiply the common denominator to each side. What you're trying to do is now make this no longer a fraction equation, right? Some of us are fractionists here. We're trying to get it so that they go away. So what ends up happening is these will cancel. So I'm just left with x plus 7. And here, when I distribute this whole term to a, what ends up canceling is the x plus 3, and I'm left with x plus 2. And when I distribute to here, my x plus 2 cancels, but b is left with x minus 3. So you can kind of see how that works, that the x minus 3 cancels for your a, so you're just left with x plus 2. And because it's getting distributed to both terms, then x plus 2 gets canceled, and b goes with x minus 3. Now that you've multiplied common denominator, now we just have a linear equation. So this is going to take some algebraic reasoning, and what we're going to do is first distribute. So I'll have a times x plus 2 times a plus b times x minus 3b. And once I distribute, notice this word right here is to regroup. And this is where we're going to want to analyze the idea of an equal sign. So here I have 1x plus 7. So a linear term plus a constant. And on the other hand of the equation, I have two linear terms and technically two constants. So you can kind of see. So regrouping it, all it's doing is allowing me to see my terms together. So again, I have 1x equal to ax plus bx, and then my constant is equal to my constant. So I just reorganized it. And what also might be helpful is if I now look, I have 1x, so a coefficient times x, and I have two different coefficients. So if I factor out x, this is now my linear term, my linear coefficient, and then this is my constant. So now if we take a look, my linear coefficient is equal to a plus b. My constant 7 is equal to 2a minus 3b. And this is where our knowing how to solve systems comes in. That's why it's in this chapter. So to figure out what a and b are based on these conditions, I'm going to say a plus b equals 1. And I can say 7 equals 2a minus 3b. And now I'm just going to solve a system. You could do it with substitution. I'm going to do it through elimination. So by elimination, if I multiply my first equation by 3, I'll just show my work real quick. So I get 3 equals 3a plus 3b. I add this across, so now I get 10. I'm going to divide by 5. And, that wasn't good, 5. So A is 2, and then to get B, 2 plus what number gives us 1 is -1. So now I have A and B. You're not done yet, although it feels that way. We're almost there. What you then have to do is remember what the whole point of this was, which was partial fraction decomposition. So now what we're going to do is take a look and see, let's rewrite it so it represents that. So we write x plus 7 over x minus 3 times x plus 2 equals, and now this is really important how you set this up. Someone else in our class could have put x plus 2 first, but what's really important is the coefficient matches. So our equation ends up being x plus 7 over x minus 3 times x plus 2 equals, and we put the a over x minus 3 because that's what we have set up for ourselves, plus, and again, we can write it as plus a -1 over. You could, and it's not wrong, to write 2 over x minus 3 minus 1 x plus 2. But sometimes that confuses people, so this is perfectly fine. I tried to break it down into steps to make it a little bit easier. Now I'm going to do one more example for us, which is when you have repeating linear factors. What a repeating linear factor means is it's no longer distinct. So again, if we go back to this, x minus 3 and x plus 2 are not the same factor. They're different. When I factor this denominator, again, I don't care about the numerator, not that I could factor the numerator here, but you're only looking to factor the denominator. Notice I get x minus 1 times x minus 1. They are not distinct. They are the same. They are repeating. How many times are they repeating? Twice, because it's an exponent of 2. So if you go all the way back to that slide where you took a picture of, you'll notice that what you're going to end up setting it up as is 6x minus 11 over x minus 1 squared equaling, and you get some number a over it. So we write it, it's almost like you're decreasing. So to the first power and then to the second power. If this was to the third, if it was to the third, just so you can see, you would write c over x minus 1 to the third. This would keep going until you have completed the repeated factors. But lucky for us, that's not our case. So this is all we have to do. And then the same process is going to happen again. We multiply by the common denominator. By factoring it, we already know what the common denominator is, so I'm going to multiply each side by x minus 1 squared. By doing this, it cancels out on the left, and then on the right, so if we actually want to kind of work the opposite way of what we normally do, this completely cancels, so we'll be left with b. And then when I distribute here, only one of them cancels, so I'd have a times x minus 1. And to make it look nice and pretty, I actually have it typed out. So again, when you distribute, I have x minus 1 underneath x minus 1 squared, so you're left with one of them. B is eliminated. Now distribute. And now you don't have to regroup here because my linear term of 6x and ax are right here. And my constants are right here. So to set up my system, it ends up being actually pretty easy now to use substitution because I have 6 equaling a, and then I have a negative 11 equaling a, negative a plus b. Please don't forget your sign. Again, how I got 6 was this is the coefficient of x, this is the coefficient of x. Again, using this idea of equals, right? Almost like a balancing in chemistry when you're balancing equations, wanting them to equal both sides. So now with substitution, I can plug this in. So I have negative 11 equals negative 6 plus b. Add 6 over, and we will get negative 5 equals b. Again, we are not done. So our final step, our final answer, you can write it, you could write from the original, you could write from here, it doesn't matter. If someone's asking just for the decomposition, they just want the partial fractions. If they want the whole thing, then you're going to write the equation. So here, x minus 1, our a term was 6, plus, and I'm going to write negative 5 over x minus 1 squared. And this will be our partial fraction decomposition. So if you want to sound super smart today, you can say you learned about partial fraction decomposition. I know I impressed my parents when I was your age saying that, so feel free to do that today. Email me with any questions. There's some work on Delta Math and in your textbook just to give some extra practice. The best way to do this is just to get your hands dirty and start doing it. I'm breaking it into just the linear today. The next video will be quadratic. All right, hope everyone's doing well and see you soon.